Hopefully by now you are comfortable with proving parallelograms, and we're moving on to now proving all the other types of quadrilaterals. To be able to do this, I can't stress enough how important this diagram is, and we've been talking about this over and over again, especially the parallelogram family. So the parallelogram family, if you know the properties of the shape above, so the parallelogram gives all of its properties to the rectangle, all of its properties to the rhombus, and then those in turn give all their properties to the square. So if this is sort of ingrained in your memory, it will help you very, very much in doing this exercise. Before we get straight into today's lesson, I want to highlight for you in your booklet on page 1 and 2, we give you a list of all the different geometry reasons that you need to be aware of. And on page 2 in particular, we have a list of the quadrilateral reasons. Hopefully you've been referring to this as we've gone through the chapters in case you weren't sure about a particular theorem or reason. But I want to show you that, and maybe you've already noticed this, all of these reasons deal with the parallelogram. And it's a little bit frustrating for some because there's relatively few reasons that deal with the other types of quads. Which can't really be the case because the other types of quads have lots of different properties as well. So you might have noticed that some of the properties, sometimes you'll be working on a problem and you're looking for a reason here that doesn't exist. If that's the case, they weren't able to list all the different properties because it just gets excessively long. So if there's a reason that's not on this list that you need, you have to use your best judgment and write something that makes sense. Always better to give more information than less information, just so that we know that you know what you're talking about. This list also includes, for the parallelograms, it includes your converses. So opposites of quad are parallel, which means it has to be a parallelogram. But notice in this one, the opposites of quad are equal. It says, or converse opposites of a palm. So we're bringing in this idea that instead of memorizing a whole new reason, you could actually just put this word converse in front of the original theorem, and that is acceptable. So it's not something that I like to do very often. I like to actually give more information rather than just writing converse. But if you're at a loss and you're not sure what to write, just write converse of whatever the property is that you already know. So focusing in, we know that our parallelogram family is the most important. Parallelogram, we've spent tons of time on the parallelogram because of this family, the parallelogram is the grandfather. It is the most important one because it gives all of its properties to the one below it. Now, to prove that a shape is a rectangle, for example, you'd have to prove first that it's a parallelogram, and then you have to prove something special to show that it's actually a rectangle. To prove that a shape is a square, for example, you'd have to first prove that it's a palm, then prove it's a rectangle, then prove something special about the square. So you have to be able to prove the parallelogram to even get to these next steps. Two ways to prove a rectangle. We're going to look at the special properties of a rectangle. So we talked a lot about what makes each shape special. In a rectangle, we know that the main thing that makes a rectangle special, its main property, is that the interior angles are all 90. So if you knew that it was a rectangle, you could then conclude that each interior angle is 90. So for example, you could say angle A is equal to 90 degrees, interior angles of a rectangle. Now the converse of that is, if we don't already know that it's a rectangle, so we know that it's a parallelogram, but we also know that one interior angle is equal to 90 degrees. And as soon as that's the case, if one angle is 90 degrees, then I can conclude that it's a rectangle. But you might be saying, don't I have to show that all the angles are 90? And the answer is no, because if it's a parallelogram, then I know that in a parallelogram, opposite angles are equal, so automatically D has to be 90. And I know that opposite sides are parallel, which means that A is co-interior, so that has to be 90, and C also has to be 90. So all I need to show that this is a rectangle is one angle to be 90, because that means that all of them have to be. So my conclusion, therefore, ABCD is a rectangle, and reason interior angle of parm is 90 degrees. Again, like I said to you before, you could just put the word converse in front of the original reason, and that's also acceptable. The other thing that makes a rectangle special is that the diagonals are equal. So you could have AC equal BD, diags of a rectangle. But now if we're using the converse and we don't know it's a rectangle, but we know it's a parallelogram, we know this is a parallelogram where AC and BD are equal to each other. So AC and BD are equal to each other, which means that it has to be a rectangle because the diagonals of the parallelogram are equal to each other. And that's pretty cool. Now proving that the shape is a rhombus. So again, rhombus comes below parallelogram. So you first have to prove that ABCD is a parallelogram. So you first have to prove that ABCD is a parallelogram. There we go. Okay. So our first property of a rhombus that makes a rhombus special is that all the sides are equal. So let's show that. My first property that makes a rhombus special is that all the sides are equal. So for example, you could conclude AD equals DC, or you could show that any of the other sides are equal to each other similarly, and that's sides of a rhombus. But now to work backwards and prove that a shape is a rhombus, if we know it's a parallelogram already, if we know it's already a parallelogram, and I know that two adjacent sides are equal, well, in a parallelogram, we know that opposite sides are equal. So that means that all of them have to have the same length. So what's nice is that you actually only need to know two sides, adjacent sides are equal, and as long as it's already a parallelogram, you can then conclude that you have your rhombus. Adjacent sides of parm equal. The other thing that makes a rhombus special, and hopefully you can remember this without me telling you, the other thing that makes a rhombus special is that the diagonals bisect each other at 90 degrees. So we could conclude, therefore, angle DEC, for example, or I could choose any of these four interior angles, is 90 degrees, and that's diags of a rhombus. Working backwards now, if I only know that it's a parallelogram, but if I have one of the interior angles is 90, then I know it has to be a rhombus. And this is because diags of parm bisect at 90. So again, like I said, if you really know your properties of quadrilaterals really well, you're just trying to work backwards to show that one of these special properties is true. Okay, the square is the one that you're going to hope you don't get asked because it can be the most difficult one to prove because it's the lowest on the food chain or on our family diagram, right? So it's at the bottom, which means that you have to show all the shapes above it. So first, you must prove that it's either a rectangle or a rhombus. Let's see how this works. The first property of a square that we know is that all the sides are equal. So we know we could conclude that any of these sides are equal to each other, sides of square. But now working backwards, let's say that we know that ABCD is a rectangle. Well, if you know that it's a rectangle, then that means you know that the interior angles are 90 But we also are given that AD and CD, or adjacent sides, are equal. And if adjacent sides are equal, then that means that it has to be a square. Because in a rectangle, we know that opposite sides are also equal. And there's my square. So you only need one pair of adjacent sides to be equal if you know that it's a rectangle to show that it's a square. The next thing that we know about the square is that all the interior angles are 90. All the interior angles 90. So you could conclude that A is 90, or any of the other angles are 90, and say interior angles of a square. The converse of that, so if you already know that it's a rhombus this time, if we already know that we have a rhombus, then that means a rhombus has all equal sides. And here we figured out, or we were given, that one of the interior angles is 90. And we know that in a rhombus, opposite angles are equal, which means that all these other angles have to be 90. There's my square. So we can conclude ABCD is a square if we know that it's a rhombus and we just have one angle equal to 90. Last one. In a square, if we look at the diagonals now, we know that the diagonals have to be equal to each other because it's a type of rectangle. So that means that AC is equal to BD. And now the converse of that, again, if we know that it's already a rhombus, in a rhombus, we know that the diagonals bisect at 90. We're given that the diagonals are equal to each other. So if I have equal diagonals that bisect each other at 90 degrees, it has to be a square. Sorry. Okay, let's see how this works, how this plays out. I'm giving you some notes on the kite and on the trapezium, but I'm not going to go through these because they're not very commonly asked. Kite and trapezium. It's a good idea for you to make sure you have these in your notes and refer to them if they ever come up. But most important is to know parallelogram, rectangle, rhombus, and square.